Okay, guys, welcome to the last in-person class, and actually, this is going to carry forward into your remote day as well. So quickly, we'll go through. Again, here is the link to the planner. And then, so this week we have Monday, Tuesday, and Wednesday. And so if your remote day is on Monday, then your in-person day is on Tuesday or whatever. You know that you're basically going to have one assignment, and that's to get ready for the final exam. And so the in-person day will be focused on answering questions that you might have during class. And the other two remote days will just be working on your problems, and then just get in touch with me if you have any questions. So the Wednesday is going to be a remote day for everybody, and then Monday and Tuesday are going to be our typical hybrid days. Okay. So then what's due? So you do need to turn in the honors review guide for the exam, and that will be due on Sunday at midnight. It's fairly lengthy. Here's the link to it right here. It is fairly lengthy, but you're going to have all week to get this done. So spread out the work, ask questions as you need, and work it through. So this slide here just shows you what you need to do to submit. And then make sure that you have access to your course companion. So the link to it is right here. Pages 1 through 60 can be very beneficial as you go through. And then also you need to have your IB physics equations. So again, they're right here. You should have bookmarked them at some point and have access to those as well. For the measurements equations, just again going through, we are going to be looking at vectors and scalars. We did look at those, and knowing that if you have an angle here and you wanted to know what the component in the x direction is, you're going to do a cosine theta. And if you wanted to know what the component is in the y direction, then you would do a sine theta. Then there's a bunch of resources in these slides as well. So here are the conversion notes and measurements notes that we did early on. So you have access to those. And then again, the vector review. And so I just kind of covered this, that if I wanted to know what the x component was, this red vector right here, it would be 6 newtons times the cosine of theta. And if I wanted to know this blue line, I would do 6 newtons times the sine of theta. I could also go ahead, and if I know what the components are and I want to know what the resultant vector would be, I can use my Pythagorean theorem and say 4 squared plus 3 squared is going to be equal to c squared, and then solve for that. And then I can take the inverse tangent in order to get the angle of theta here. So then also when we add vectors, remember that we need to break them up into their components, so that we need to look at what the x component of this vector is and the y component. And then if they are offset, if they are, like in this case, the red arrow is pointing to the right and the blue arrow is pointing to the left. So we're going to subtract the x components of those vectors. Both of them are angled upward, and therefore we're going to add those components together, and the resultant would be this black line right here. So the x components canceled out, and the y components just added together to give an increased vector that's going due up. Our kinematics equations, make sure that you realize what all the letters here mean. That's one of the biggest problems that students have, is understanding what V stands for, what U stands for, what A stands for, what T stands for, and then being able to manipulate these formulas and plug in the correct letters here. Additional resources for you. These are optional resources, but again, if you're looking at a topic and you're just really struggling with those, then these 3 things right here will give you some additional resources for those and help you out along the way. And then also here we have the velocity notes, the graphing motion notes, horizontal projectile motion notes, angled projectile motion notes, and then 1D kinematics. So there are a lot of resources here for you, and then also the 2D kinematics, which was our projectile motion. So a lot of resources there for you to go back and look at. And then making sure, and I think this is one of the biggest things, is that you understand how to approach a problem. Sketch out your free body diagram. Make sure you list your known variables and variables that aren't given to you specifically, like if it say something is dropped, that you understand that you're dealing with gravity, and that you're dealing with, if it's dropped, that the initial velocity was 0. So things like that, making sure you can identify those, and then knowing what the problem is looking for. What is your unknown? And then going through and finding your correct formula that is going to get you the right answer, and then manipulating that formula, plugging in your numbers, and then calculating what your known answer is. Okay, so we're going to quickly go over some of the topics that we covered this quarter. And so the first thing we're going to go over is kinematics. So in kinematics, we talked about the difference between scalars and vectors. So in this case, this blue dotted line represents distance, which is a scalar, and this black line represents displacement, which is a vector. And so again, a scalar is just going to be magnitude. And in this case, the magnitude is going to be all of this distance added up. And our vector is going to be displacement, which is just the straight line distance between these 2 points. So again, distance is a scalar, it's just magnitude, and displacement is a vector, it is direction and magnitude. So then we come over here to speed and velocity. So again, speed is a scalar and velocity is a vector. And just looking at this car going around a corner, this car can be traveling at a constant speed, but if it is, it's not traveling at a constant velocity as it goes around this corner. So as it goes around this corner, it's changing direction, and because of that, it is changing its velocity, which means it's accelerating, and that's an important thing to understand. Speaking of that, here is acceleration here. So again, as something is going around in a circle, even though its velocity, the speed aspect of its velocity is not changing, it's accelerating, and it's accelerating inward because it's changing its direction as it goes around in a circle. So again, that vector idea is very important to include direction. When we looked at our displacement versus time graph, again, so if we look at a slope here, if we know what that slope is, the slope of a displacement versus time graph is going to give us our velocity. And then if we look at the negative slope here, that's going to tell us that we're going in a backwards direction. And then if it's flat like it is here, that's telling us that we are having 0 velocity. So here we have a increasing velocity, but at a constant rate, a decreasing velocity, but at a constant rate, and then no velocity right here. And so again, the slope is that idea, the derivative that tells us what that velocity is. Then we had a velocity versus time graph. And so again, when you're doing these motion graphs, understanding what is on the y-axis versus time. So in the first case, we had displacement, so position change versus time. In this case, we're talking about velocity versus time. And so when we look at a velocity versus time graph, if I look at the slope of this, now I'm going to be talking about acceleration. So this right here is showing the acceleration. But then the other side of that was that I can look at the area under the curve, take the integral, and if I calculate the area under the curve here, that is going to give me my displacement. So it's important that you understand the difference between what the slope is and what the area under the curve is. Okay, so the integral again is that area under the curve. In this case, we have an acceleration versus time graph. And here, when we do these, we're going to always have constant acceleration. And so in this case, we have a positive constant acceleration, and then it drops immediately to no acceleration. And then over here, we have a negative constant acceleration. So we will have constant acceleration problems. And again, the area under the curve. So if I calculate the integral of this area under the curve here, that is going to give me my velocity. Okay, so important to note that. And then understanding these equations. So again, knowing what the letters are, V for velocity, U for initial velocity. So the V for final velocity, the U for initial velocity, A for acceleration, T for time, and then S is going to be our distance or our displacement. So important that you know what those letters stand for, and so you can identify them and then manipulate the formula to match what you're looking for. Okay, then we briefly got into projectile motion, and we looked at projectiles being launched up and then coming back down, and recognizing that there was a symmetry to this arc, and that at the height, the highest point that the projectile reaches, that it had zero velocity in the y direction, but that along the entire path, the velocity does not change in the x direction. Again, this assumes that there is no air resistance, and so when we do projectile motion, we always say in the absence of air resistance. And then so if there is no air resistance, there will be symmetry that we can follow here. And then again, the height at the highest point, there will be zero velocity in the y direction, but along the whole path, you will have the same velocity in the x direction. The velocity in the y direction will change due to gravity. That's the only thing that will be acting on it the whole way. So it will be slowing down on the way up and accelerating on the way down in a negative direction. And then when we look at the velocity that it's launched from, so if the projectile is launched at some velocity v, then we need to break that apart into its x and y component. So the x component will be v cosine theta, and the y velocity will be v sine theta. And so if we looked in and we asked, well, what's the velocity here at its highest point? Well, we already said that there's no velocity in the y direction. So it would be v cosine theta would be the entire velocity of that projectile. If I look at the velocity it's launched from here, that will be equivalent to the velocity it lands with over here. And then so these are just some of the things that we're looking at with projectiles. Now, mostly we just spent our time looking at horizontally launched projectiles, but you do need to know to break apart the x and the y components for your projectile, and that the x velocity doesn't change, but the y does. Okay. Then we have to look at if there is air resistance. And so the blue dotted line represents in the absence of air resistance, so our typical projectile. And then in the real life scenario, there is air resistance, so it's going to slow it down. So it's not going to allow it to get to as high a height. And because it's slowing down, it's also going to be slowing down in the x direction. So you get this kind of a squashed shape over here. So it's not going to go as far nor as high, and it won't spend as much time in the air either. Then we look at the vertical velocity and the horizontal velocity. You can see that they're both affected by air resistance. So then this one represents that tabletop lab that we did. And so if a projectile is launched horizontally and we want to know where it landed, we need to first, again, break apart the x and the y component, realize that the only thing that transfers between them is time. And so the time that this is going to be in the air is going to be used to determine how far it's going to travel. And so to do the time in the air, we're going to use that 2 times the delta y, and then divide it by gravity and take the square root of that. And that's actually worked out for you right over here. So to find the time, you take the square root of 2 times the change in the y divided by g. And then, so this is actually done for that tabletop one. And we came out with about 0.39 seconds. And then you're going to input that time, and you're going to use your velocity in the x direction to determine how far it's going to travel. So that's worked out for you right here. And you can look that over again. And I recommend looking that over again. Last unit in dynamics is a little bit tougher than the other ones. More people seem to be struggling with this unit. So first off, our formulas for Newton's second law, F equals ma, and then our forces of friction for both static and dynamic friction, whether it's stationary or moving. Then we come over here, lots of other resources for you, so notes and things that you can look at, and then here are some worked out problems that you can look at for this area if you're having issues. Then coming over here, there are some videos here. It's all these videos over here, and you can kind of fast forward as you go if you are interested in getting a little bit more information on these topics. And then we have all the notes. So here's Newton's first law and free body diagrams, followed by forces and inclined planes, friction notes, Newton's second law, and then we get to free body diagrams. And so a lot of students are having issues with free body diagrams. And again, just kind of realizing that when you are drawing an object, you find the center of mass, and you are going to draw all your forces from that. So your real forces are drawn with solid lines, and then your component forces, your ones that you're going to break into the X and Y direction, will be drawn with dotted lines. And then you assess to see if it is an equilibrium or a non-equilibrium. And then some coming over here, using Newton's second law, we're going to kind of look and assess whether or not it's an equilibrium or if it's going to be accelerating because it's a non-equilibrium. And then we have to remember that when we have a force at an angle, that we need to find the X and the Y components. And so we're going to use our sine theta and our cosine theta for those. So here's the inclined plane example. And so remember that on an inclined plane, we're going to be tilting our axis so that when we're looking at this one, we're going to tilt our axis in this direction so that this is going to be our X and this will be our Y. And that's so it's easier to align our forces so that 2 of the 3 that are acting on this object right now will be in our XY plane. And then the third one, the weight of this object, will just break the components into our X and our Y. And that's what you were supposed to memorize, that if I look at this object right here, that when I break it into its components, and I think that's on the next page, so I'll come here. So when we look at the mass of it, when we do the mass or the weight in the Y direction, that's going to be our mg cosine theta, and that is going to be balanced off over here by the normal force. And then our friction force is going to be acting to the left in this example, and then to the right, we're going to have our mg sine of theta. So then here's an example of a problem going on where this person falls into the net. And as they fall into the net, they are decelerating. So they're slowing down, which means the net is exerting an upward force. And because they're slowing down, that upward force is greater than the downward force. And so you're going to assess what the force, the upward force of that net is. And so it turns out to be Fn equals m times a plus g, and that problem is worked out for you here. So using a free body diagram, again assessing that the normal force exerted by the net is greater than the downward force of weight, and then you say the sum of the forces equal mass times acceleration, and then excuse me, those sum of the forces are going to be the normal force minus the weight, and then you're just going to solve for n, and you can see that you get your answer here. Couple more problems. So here's one where, again, we did this one in class where an object is being pushed down an inclined plane in the absence of friction. And in this case, it's asking what is the force here. So if we set this equal to MA, we're going to say that the two forces acting on this are the weight in the X direction, which is going to be your mg sine of theta, and then the force of this. And that is going to equal our mass times our acceleration. And we're going to solve that out, and it's done for you here, where again, the sum of the forces equal mass times acceleration, the force plus that mg sine of theta, and then you're going to just solve for force and subtract out your mg sine of theta, and you're going to get m times a plus g sine of theta for the force. For the other one, you have two dogs wrestling for a bone here. One's pulling one way, the other's pulling the other way. This bigger dog is going to be pulling with the greater force. Normally, left is going to be our negative, and to the right is going to be our positive. So the smaller dog here is pulling to the right with a smaller force. So when we subtract out the force of this bigger dog, we're going to get a negative acceleration in the direction to the left. And that's worked out for you right here. So you see a greater force in the leftward direction. And so you end up getting an acceleration of F of S minus F of B divided by mass. And then one last problem over here. You have a 2 kilogram box that is at rest on a table. Excuse me. And the static friction is 0.4. Kinetic friction is 0.2. A 25 Newton horizontal force is applied to the box. What is the estimate of the magnitude of the box's acceleration? So if the box is accelerating, that means it's moving. And at that point, we're going to use our coefficient of kinetic friction. And so this is the number that we're going to use when we're getting the acceleration. And so once again, that problem is worked out for you here. And you can see right here that the coefficient of kinetic friction being 0.2 is the number that's used because it is in motion at the point that it's accelerating. So initially you would use the static friction when it's at rest to get into motion, but once it's moving, then you need to use that kinetic friction for coefficient. Okay, and that's it. So we will have time to work on problems in class and come with any questions that you might have.